Hello everyone. In this video, we will see how to optimize the isPrime function. That is to find if a given number is prime or not. In the last video, we used this basic version where we were checking for all numbers from 2 to n minus 1, and we checked if the remainders of n with these is 0. So here's the code for the same. Prime equals 2 for j equal to 2 less than or equal to input minus 1. If the remainder is 0, you make it false, and now let's just run it for all numbers between 2 to 10,000 and see how long it takes. As you can see, it's taking quite a while. Now we want to be able to improve on this. So one very intuitive idea is that since 2 is the only prime even number, we can skip checking 4, 6, etc. And that's version 2, where you just check for 2 and then you don't check any other even numbers because that's unnecessary because we will be checking with all the other odd numbers anyway. So if we do this, in the earlier version, if n was 10,000, we got around 9,998 checks. But if we do this ignoring all the other even numbers, we can reduce the number of checks to 5,000, which is 2x improvement. Now let's just do the same. Now let us implement v2. So first we need to check if it's divisible by 2. So I write an if condition for that if input percentage 2 equal to 0. Of course, you can handle the corner case where input is actually 2, but I'm choosing not to do that. So I will change in the main from 3 to 10,000. And yeah, we'd return that it's false. Then here we need to change from 3. And then because we need to look at only the odd numbers, I should jump by 2. So j plus equal to 2. Everything else is fine. So this code should work as it is. And so you can see that it runs much faster than the previous version and it gave the correct output. So yeah, that's version 2. Even though this was actually faster than the naive version 1, we can actually still do much better than this. And to understand how, let's go to this page. 10,000 was the case we were dealing with, right? So 10,000 is nothing but 100 times 100. Now, let's just say I increase A to 101. If I increase B, will I be able to get 10,000 or should I decrease B from 100? Obviously, I should decrease B. Now, the same holds for B also. Maybe I make B some 105, 106 or something. If I increase A, will I be able to get 10,000 again or should I decrease it? I should obviously decrease it for it to come closer to 10,000. Now, I don't know if that rings a bell, but what is essentially happening is if I'm looking at a number 10,000, then any one of its factors must be less than or equal to 100. Both of them cannot be greater than 100. And that's a crucial point. So if let's say it was 103 times 97 or something, if you had checked if 10,000 was a divisor from 1 to 100, you would have already checked for 97. So you don't need to check for 103 again. And this is the point we will be using. So to check if 10,000 is a prime number or not, you don't need to check from 3 to 10,000 or 3 to 9,999. You can only check from 3 to 100 or 3 to 99. That should be more than enough because if it any one of its factors is greater than 100, the other one would have been lesser than 100 and you would have noticed it already. Now this brings up a huge difference in the number of checks you do. So in this case, you would only still check till 99. So you from 5,000, you reduce the number of checks to just 50. That's a huge 200 times improvement. Now let's code the same and check it practically. Now let us implement the square root version in code. I'm using a different online code editor because the previous one which I was using didn't allow the inclusion of math.h, which is needed to calculate the square root. Or of course you can write your own function to calculate a square root, but I thought this would be easier. And so this is the code to get the square root. Because square root function handles in double inputs, I converted input which was an integer to a double, and the output of square root will also be a double. That's why I'm using int to convert it back to an integer. And then the rest of the code remains the same. We check if it's divisible by 2, and then we look at all odd numbers only till the square root. So instead of input minus 1, I made it final. And you can see this ran instantly.